Okay, so last class we looked at limits from a graph and limits from a table. What was the y value that was matching up from left and right? But I didn't necessarily just give you a function and say, look at this function and tell me what it is. Well, that's what limits analytically is. It means we're working with a function, a y equals something. And we're not going to necessarily look at the graph, although we could, but it's an extra step. Now we just want to be able to look at just the function and determine what the limit is. Well, the very first thing you always try is just plug in the number that we're trying to find the limit at. So I take this number, I plug it in for x, evaluate the function. If I get an answer, that's the limit. That's the y value, that's the answer. Okay, that just means if we have some graph, there's no hole, there's no asymptote, there's no jump. So if I look for a limit, at that point, it's just the y value that goes with it. So sometimes that works. So we're just going to start evaluating some of these, okay? What is the limit as x approaches 2 of 3? So think about this. This is the function y equals 3. What does that look like on a graph?
It's just a horizontal line, right?
It is a horizontal line. All y values are 3. So there's no x value to plug into it. It doesn't matter what x is. We always get 3. So the answer to this is 3.
Couldn't you put all real numbers?
No, that would be the x values. That would be the x values. Remember, a limit is a y value. Okay, now the limit as x approaches negative 4 of x. So we take this value, we plug it into the x, we're going to get negative 4. Okay, this one is just the line y equals x. So if we go 1, 2, 3, 4, 1, 2, 3, 4, that's what we're going to get. They're going to match up. It's a y equals mx plus b. Slope's 1, y-intercept 0. That's what we get. Okay, limit as x approaches 2 of x squared. So we plug in a 2 for the x, we square it, and we get 4. Easy enough, right? Okay, if I do the limit as x approaches 2 of 4x squared plus 3, all right, there's some properties that they give you for limits. I'm an engineer. I'm all about application of math as opposed to theory of math. I don't need to teach you the properties for you to be able to do this. There's a property that says, oh, well, so you evaluate this one as a limit, and you evaluate that one as a limit, and then you add them together. Doesn't that seem obvious? I don't need to teach you that and make you write it down for you to be able to do it. It's direct substitution. We plug in a 2, and we get 4 times 2 squared plus 3 is 16 plus 3 is 19. All right, limit as x approaches 1 of x squared plus x plus 2 over x plus 1. So we're just starting to get a little bit more complicated functions here. It's still always going to be direct substitution. So I have 1 plus 1 plus 2 over 1 plus 1 is 4 over 2, which reduces to 2. Then we have the limit as x approaches 0 of the square root of x squared plus 9. So again, just direct substitution. We end up with the square root of 0 plus 9, which is the square root of 9, which is 3. Okay, limit as x approaches 3 of the cube root of 2x squared minus 10. Direct substitute. We got the cube root of 2 times 3 squared minus 10. 3 squared is 9. 9 times 2 is 18. 18 minus 10 is 8. What's the cube root of 8? 2. Okay, now, in calculus, I've told you there's a couple of things that we do. We don't use mixed numbers. We stay in radian mode. You always give exact answers. Exact answers mean you don't plug it in your calculator and round. Okay? I've had students, it's mostly when I taught high school, who think that if you write down every decimal place the calculator gives you, that's an exact answer. No, it's not. If this had not been a perfect cube, if it had been the cube root of 10, that's what you would give me as your answer, is the cube root of 10. You simplify as far as you can, but you don't put it in the calculator and round. Okay? So this one happened to be a perfect cube. It came out nicely. Okay, the limit as x approaches 0 of tangent of x. Well, for me, on the unit circle, I've got sine and cosine memorized. I don't have tangent memorized. So I'm going to write this as the limit as x approaches 0 of sine of x over cosine of x. Because I know what those are. And tangent is sine over cosine. So that gives me sine of 0 over cosine of 0. What is sine of 0?
0.
It is 0. What is cosine of 0?
1.
So 0 divided by 1. If I have no pizza, how much does one person get? None. This is 0. Okay, now this is the first time I wrote down limit as x approaches 0 in a problem. Sometimes you're manipulating the problem and you haven't done a direct substitution yet. If that's the case, you keep the limit notation until you've done the direct substitution. And I'm really picky about this because that limit notation, it's a command. And that command is saying, plug this value in for x. Once you've done the command, you lose the notation. So as long as there's an x still in the function, you keep the notation. And as soon as you plug it in, you lose the notation. Right? If I tell you to do 2 plus 3, you write down 5. You don't write down plus 5 because you've completed the command, so then you lose the notation. Okay, limit as x goes to pi over 4 of sine squared x. So what we're looking at here is sine of pi over 4 all squared. Notice, don't have an x in there anymore, so I've lost the limit notation, right? I've done the direct substitution. What is sine of pi over 4?
Root 2.
It is root 2 over 2. When we square that, what do we get? 2 over 4, which is 1/2. Okay? Limit as x goes to -1 of x times e to the x. So we direct substitute. I can lose the limit notation now. Negative e to the -1. And WebAssign's going to take that answer. If it doesn't, you need to tell me. But if you were doing it in the textbook, or if you did try a similar problem or practice another version in WebAssign, they're not going to make the answer look like that. They're going to make it look like -1 over e. As long as your answer's simplified, that's good enough for me on a test. Okay, so like going back to this problem over here, I would not take 2 over 4 as an answer. I want a simplified answer. I want 1/2. But in this problem, there is nothing different between the value in both of those answers. So I would take either. And just because you do the practice another version in WebAssign and it makes the answer fancy doesn't mean you have to make the answer fancy. But they will always show you the most complicated answer. They will always go an extra step to make it look harder than it is. Okay, limit as x approaches e of natural log of x cubed. Well, that's a little bit complicated. I'm going to use the properties of logs to make this easier on myself. If I didn't, I still eventually would come to the same answer. At least I hope you would figure out how to simplify it. This would be a case where WebAssign would not take the unsimplified answer if you didn't realize how it could be simplified. The power property tells me I can bring that exponent in front of the natural log. So before I do the direct substitution, so I'm keeping my limit notation, I'm going to rewrite this as 3 times the natural log of x. Then I'm going to do my direct substitution, so it's 3 times the natural log of e. And what's the natural log of e? What is the base for natural log?
The base is e.
The base is e for natural log. Common log, it's 10.
Common log is 10.
Okay, so this is basically saying e to the what equals e? 1. So that goes to 1, and we have 3 times 1, we just get 3. Now, if I had written it differently, if I hadn't moved the 3 before I started and I just did direct substitution, I would have ended up with natural log of e cubed. And WebAssign's not going to take that. That's not a simplified answer, right? Because the answer is 3. And if I hadn't used the power property, I wouldn't have seen, oh, it's natural log of e, which simplifies to 1. So that's why I did what I did. Okay? Now I got the limit as x approaches 0 of x squared minus 4. So that's the square root of 0 minus 4. equals the square root of -4. Now think about what we're doing here. We're looking for a y value on a graph. Can I plot the square root of -4 on a graph? No. Imaginary numbers are what they are. They are a thing. They are important in math, but I cannot plot them in the xy plane. So since I cannot plot this number, this limit does not exist. There is no y value for the graph of y equals x squared minus 4 at x equals 0. And I abbreviate does not exist, DNE. I think WebAssign makes you type out the whole words. It doesn't? It takes DNE?
It doesn't say DNE.
All right, perfect. Okay. Limit as x approaches 0 of x minus 9 over x. So I'm going to get 0 minus 9 over 0, which is -9 over 0. Am I allowed to do that? Now, what would that look like on a graph?
Vertical. Is it a vertical line?
It's an asymptote, a vertical asymptote. So it would be that dashed vertical line. Okay, so if I plotted it, it's a nice, pretty graph, actually, but at 0, it has a vertical asymptote. But, again, we can't plot imaginary numbers. We can't plot dividing by 0. That's not one specific y value on the graph, so this is a does not exist. Okay, this next one, a little more complicated. Limit as x approaches -3 of x squared plus x minus 6 over x plus 3. We'll do a direct substitution. Get -3 squared plus -3 minus 6 over -3 plus 3. So this is 9 minus 3 minus 6 over 0. 0 over 0. Not necessarily. Okay. Okay, so what happens when we have a rational function, meaning there's a numerator and a denominator, and we get 0 over 0, or infinity over infinity, which we're not going to deal with today. It's called an indeterminate form. Usually, almost always, that limit is going to exist. Because whatever's making the numerator equal 0 is also making the denominator equal 0. And I can simplify it out, and it'll be a whole. Almost always. So let's go back to that problem. Direct substitution gave me 0 over 0. So I have to try something else. One of the methods to simplify is to factor, okay? So number 1 is direct substitution. Well, we tried that and it didn't work, okay? And it just depends on the problem which one of these other methods I'm going to try. I see something that's factorable here, so I'm going to factor it. So here's the type of problem where I'm going to be really picky about your limit notation. I can't do direct substitution until I simplify this thing. So I'm keeping my limit notation until I've plugged in for x. If you put an equal sign between two things that aren't equal on the test, I'm going to mark it wrong. It's math. They have to be equal. So you need to keep your limit notation until you do the direct substitution. Now, in the numerator, I can factor this. What multiplies to -6 and adds up to 1? -2 and 3. So this is x minus 2 times x plus 3 over x plus 3. And if you need help with your factoring, trying to figure out what it is, you need to think about the fact we're trying to simplify the denominator with something in the numerator. So x plus 3 was going to be a factor if this was going to work. So that goes to 1. And we have the limit as x approaches -3 of x minus 2. Now I can do a direct substitution and drop the limit notation. I get -3 minus 2 is -5. So if I were to look at this on a graph, it would look like a line with a hole in it, right? And I know that it looks like a line because the simplified version looks like a line. But it would have a hole at -3. Okay. Limit as x approaches 0 of the square root of x plus 1 minus 1 over x. We do a direct substitution. And I get square root of 0 plus 1 minus 1 over 0. Well, that's 1 minus 1 over 0. We've got 0 over 0. So there must be 99% of the time a way to simplify this. So we've got yet another method that we're going to learn here. And oops, I'm wrong about that. We're going to use the conjugate of our square root and number term to manipulate this. I started to write complex conjugate, right? Because that's what you're used to, right? If you remember all the way back to college algebra and you had to simplify a denominator that had an imaginary number in it, you multiplied by the complex conjugate. Okay, so the conjugate of a term with a radical in it is the same idea. We change the sign in between the parts of it, right? So if you think in imaginary numbers, if we had a plus bi, the conjugate was a minus bi. Anytime you see a square root problem, and one of the problems in WebAssign in the homework for this is even going to give you a hint and tell you to multiply by the conjugate, you multiply that, because what this is creating is a difference of squares. When I FOIL this out, it's going to square the square root, and it'll eliminate the middle terms because it's a difference of squares. So I'm going to get rid of the square roots. Notice I am keeping my limit notation because I have not done a direct substitution yet. So when I multiply the first term together, square root of x plus 1 times square root of x plus 1 is just x plus 1. If I multiply the outer terms together, I'll get square root of x plus 1, but then the inner terms give me minus square root of x plus 1, so that cancels. That's why we're doing it. And then when I do the last, I get -1 times +1 is -1. Oh, I totally screwed up. This was the one video I needed to correct for what I had online, and I've messed it up. Anybody have a clue what I've done wrong?
You did a plus when you use the conjugate, you had a plus on the second part.
Well, that is the conjugate. That is not what I've done wrong.
You can start a new
Is that the
video.
same thing on the bottom?
Hmm?
You can start a new video.
Oh, I can, I don't,
Pause it and press play again.
yeah, I'll have to cut it and do things. It's okay. I'll just leave the old video up for a while. The only thing wrong in the old video is I spelled indeterminate wrong in it. Okay. Okay, so let's fix this. For my denominator, we're going to multiply by the same thing because we have to be multiplying by a fancy form of 1. We've done the numerator correctly. In the denominator, I'm not going to do anything. I'm not going to distribute. I'm just going to rewrite it. Okay, now think about this. When we factored, we wanted to turn the numerator into something that was going to cancel with what made the denominator 0. So since this x is what's making the denominator 0, I don't want to distribute it. I need it to cancel out. So the part that I'm not trying to manipulate, I'm going to leave it be. Okay, so then notice this is going to turn into the limit as x approaches 0 of, well, 1 minus 1 is 0, so we just have x over x times the square root of x plus 1, and x over x goes to 1. So we have the limit as x approaches 0 of 1 over the square root of x plus 1, and now I can do direct substitution. I get 1 over the square root of 0 plus 1, well, that's the square root of 1 plus 1, which is 2, right? So I'm going to get 1/2. Okay, so everybody understand where my mistake came from? And now it's fixed. So when you see a square root in a problem, after you've determined that it's 0 over 0, because you always want to do direct substitution first, I will put problems on the test that look just like this, but when you plug in, you don't get 0 over 0, you just get a number. So you want to always check first, and if you get 0 over 0, then you go forward. Okay. Go back? Yes. So the next problem is written the way it is in no math book ever, including yours. But it looks this way in WebAssign, so I wrote it this way. What does a -1 exponent mean? Move it to the bottom, right? It's a reciprocal. It's 1 over. So the first thing we're going to do here is rewrite this thing as the limit as x goes to 0 of 1 over x plus 4 minus 1 over 4 all over x. Because that makes more sense to work with, right? When I plug in the 0, I'm going to get 1 over 4 minus 1 over 4 over 0, we get 0 over 0. So this is going to be our fourth method. When I have complex or compound, means the same thing, fractions, which is a fraction inside of a fraction, we find common denominators, we get rid of it. When you have problem, and there's even a problem in your homework that just has two different fractions in it, they're not even compound, find a common denominator. When you're working with fractions, you either want to put them together or separate them. In Calc 1, it's usually put them together. In Calc 2, it's usually separate them. So, looking at these two fractions, what would my common denominator be? It would be 4 times x plus 4, right? I would multiply the first one by 4 over 4, and I would multiply this one by x plus 4 over x plus 4, correct? Okay, now, I'm going to save myself a step, because if I combine these fractions and I get a common denominator, then I'm going to have to flip and multiply, right? Well, you can cut that step out if you will just take the whole thing and multiply the top and bottom, numerator and denominator, of the big fraction by what would have been your common denominator. It's just going to save me from flipping and multiplying and then simplifying later. It just saves some steps. Okay, so what happens now is I have to take this whole thing here and distribute it to both of these fractions. Well, when I multiply it by the first fraction, I got 1 over x plus 4 times 4 times x plus 4. Those x plus 4s cancel, correct? So I keep my limit notation, because I haven't done direct substitution yet. The x plus 4's cancel, and I get 4. When I multiply by my second fraction, the 4's are going to cancel, and I'm going to get minus x plus 4. And remember, this x here is what we want to cancel out in the denominator, so I'm not even going to distribute or do anything. I'm going to hope that it's going to simplify out. Okay, so I put parentheses around this x plus 4 because I want to make sure that I distribute this minus to both of them. And I'm going to get 4 minus x plus 4. Well, that's just minus x. And negative x over x is going to go to negative 1, right? So I got rid of that thing that was making my denominator equal 0. And now I have the limit as x approaches 0 of negative 1 over 4 times x plus 4. We do the direct substitution. I get negative 1 over 4 times 4. So the answer is negative 1 over 16.
On that red section right there in the center,
Mm-hmm.
where'd you get the times for x plus 4 stuff?
I looked at, okay, so we're going back up to right here. And I said, what would be the common denominator of those two fractions if I was trying to combine them? Well, I'd end up multiplying this one by 4 over 4, and I would have to multiply this one by x plus 4 over x plus 4. So that's what the common denominator would be. So I just want to get rid of the denominators, so I multiply by it, and it makes them go away. Yeah.
Whenever you cancel out the x's, would that be 3x though?
Okay, so I told you that almost always, when you have an indeterminate form, you can get a limit out of it. You can get a y value. But every once in a while, there's a case where it doesn't happen. Not going to happen in your homework, and it's not going to happen on your test. But I just want you to be aware it doesn't always work out. So if I look at this problem, limit as x approaches negative 3, x squared plus x minus 6 over x squared plus 6x plus 9. First thing I'm going to try is direct substitution. I'm going to get 9 minus 3 minus 6 is 0. 9 minus 18 plus 9 is 0. So we have an indeterminate form. So when you look at this one, tell me, what method would you use to approach it? Factoring. All right, and this happens to be something we factored before in the numerator anyways. So the limit as x approaches negative 3. What multiplies to negative 6 and adds up to 1? Yeah, we did that earlier. And then in the denominator, what multiplies to 9 and adds up to 6? 3 and 3. So one of those simplifies, and we're left with the limit as x goes to negative 3 of x minus 2 over x plus 3. And now we will try direct substitution. So I plug my negative 3 in. I get negative 3 minus 2 over negative 3 plus 3. We get negative 5 over 0. Now that happened to us much earlier when we were just doing a straight up direct substitution. And so what would that look like on a graph? What would that be? A vertical asymptote. Okay, so that one didn't divide out. So we would say what for the answer? Does not exist.
So anytime you do more than one method and it still comes out to not a limit, it doesn't exist?
A number over 0 means I can stop working and it does not exist.
Okay.
0 over 0 means keep working. Pause here for a second. Okay, so there's this thing called the squeeze theorem. I would not write this down. You're going to get to watch the video later, or you can print out the notes. Anything that's written here before I write on it is in the notes that you can print out for yourself. So what it says is if I have a function that is in the middle of two other functions for all values of x, except maybe the one on x, maybe there's a hole there or a jump discontinuity or something like that. But for the most part, this function, so let's look here at my function f. See how all my values, it's squeezed in between the other two functions. And they all meet up at the same y value at this x value for c. Okay, well, if I know what g is, the upper function, and I know what h is, the lower function, and I know they are the same, so both of their limits as x approaches c are the same y value, and I know the other functions in between them, then obviously its limit at that x value is going to be the same, right? Because it's in between the two and they're the same. It's obvious, right? I mean, it's very logical. Okay, so we'll do an example. And there's maybe 2 of these in the homework. You would just work them just the same way. But the application of it, you know, if you ask me why do we do this, I cannot tell you. In my experience as an engineer, I haven't used it. But it's something we do. So if I want to find the limit of a function I don't know, but that function is in between these other two, then I take the limit of the lower one and the upper one, and if they match, that's the limit of my function. So we're going to do the limit as x approaches a of b minus the absolute value of x minus a. We just do a direct substitution. We get b minus the absolute value of a minus a. Well, that's just 0, right? So we get b. Then I'll do the limit of the upper one. So now I'm going to do this one. The limit as x approaches a of b plus the absolute value of x minus a. Do a direct substitution, and we get b plus a minus a is 0. So we get b. So if my higher function is b and my lower function is b, the one in the middle must be b.